All right, everybody, thanks for coming. Now, it's kind of hard to give a solution to an exam when practically everybody had a different exam. But for number one, pretty much you had something that looked like this, or its opposite. Okay, we're recording, okay. And just let me finish my thought and then I'll answer your question. So this is the time axis. And really, when these times occurred would be different, and then how high, and then what the slope is would be different. And it's mostly people are getting it correct. Sometimes what I think is it's being marked wrong, right? Where let's say this first one was 2 UT, right? The first, like that happened at 0. Well, yeah, in an equation format, you just put 2 UT. But in my open math, it would be 2, using the multiply symbol, UT. Now I can see that by hand, and I just, so it seems that a lot of people did that where they just entered it in wrong because maybe this symbol is missing. But I can tell that it's right. All right. And other things, like let's say somebody did something like this, where you have an extra parentheses. I can tell that that's a typo, right? But the rest of the equation is correct. And so then your score would go up. But so it depends. Okay, so so no, I've probably only done 10 so far because I have to look at the mom, see whether it's right or wrong, then look at the answers that you wrote to make sure that you actually you documented your work, right? Or again, it can help to detect typos. But the thing is if your answer's correct in mom, I can rapidly grade that answer and move on. So the fact that there's both will, it's also, you're entering it in twice so that the chances of getting it correct are, I'll take, it's not like you can put click low pass and on the paper put high pass and I'll take both. But what I'm saying, it actually paints a bigger picture so that I can get to yes more easily. All right. So like, and for instance, on number 5, right, you were able to select, which plot it was, but the reasoning, right, is all set to 0 because I have to grade that by hand anyway. So everybody lost 10 points right off the bat, right? Now your reasoning might not be persuasive, but the highest you could get on this exam would have been a 90 before I went in and hand graded it. Yeah, just a minute. Now now that I see the chats, I noticed that sometimes people are sending a chat and they don't really want me to answer it. It's for everybody. And so what I'm thinking that is if in the chat, if you really don't want me to answer it, or you're just, being emotional or anything, just maybe put A for all or all, right? you know, all something, 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 right? Then I know it's not for me, right? Now, sure, sometimes if somebody's doing this one, I know that that's not a question, okay? Maybe if it was for me, you could put P for professor or something, I don't know. But then I know to ignore it. I think I turned private messages off so that I don't forget to do it during an exam. Oh, yeah, private message to me. Yeah. Okay. So, so that's basically number one. Number two, and then usually, let's say you got this one, this one, this one. So there's like 4 things to consider, right? Mom, it's right or wrong. But if you got 3 out of 4, I try to give partial credit for as many as that you got correct. All right. Which mom can't do that, right? So in general, your score goes up. However, on plots, mom can give more points than are really justified. Now, let's just take a Bodie plot, right? And let's say you're at 2K, right? And then this is 200, and this is 20K. It's very easy to draw this on a piece of paper, right? But trying to get that point exactly where it should be is, I couldn't do it. So I just look and say, all right, that's close. And then I give the points. All right. Now, so far, you know, if you have S squared, right, that phase is going to go from 180 down to 0. However, you could have a repeated pole, right, where let's call that A, and that's A divided by 10, and 10 times A. You could have a version where the poles are separated by 100, where this would be A divided by 10, and this would be B divided by 10, times 10. Right, it just pushes the curve out, right? And then it could be really far apart where the phase did something like this, right? And yeah, if it's a low pass, it starts at 0 and goes to minus 180. Some common mistakes on magnitude, although it's possible to have a Bodie plot like that, low and high pass filters do not do that, all right? You would need like a pole, a 0, not at 0, to get that kind of action, all right? But so those were the 3 kinds of plots. And again, the phase would have been the same, except instead of 180 to 0, it'd be 0 to 180 for the high pass, where you would have like A squared, right? And whatever gain, right? Now the magnitudes, right? For the high pass, right, you could have a sharp slope, then the slope evens off and does that. And that's for 2 different poles, right? You could have this, and that's at 40, and that's where the pole is repeated. And the thing is that's plus 40, that's plus 20, and then the slope evens out, right? For the low pass, right, it would be 40 if the pole were repeated. right? And then if you had two distinct poles, right, you would have something like that. So really and so actually when I'm programming the right answer for the low pass filter, this curve is the same, and I just change the numbers over here, right? And then whether it's close together or far apart, all right? Now again, I assume you might want to see me and talk about your exam in particular. I am trying to give little hints as to what is wrong, and it might sound kind of harsh, but it's really just like quick notes. This phase does not go from 0 to 180, right? A very quick note. But if you need more help with that, you know, I'm happy to talk about that. Okay. So number 3 was basically right off the midterm practice, right? You had a high or a low, except on the practice, everything was, you know, omega naught was like 1K, 10K, 100K. On the exam, you could have, I think it was 1, 3, 5 scale factors. But pretty much it's the same, right? H of S for a low pass filter, you're going to have that gain, whatever that happens to be. They're all first order, right? I noticed some people put things in a different format, but algebraically it was the same. So mom said it was okay. So I'm like, fine, right? And then for the Bodhi plot, right, what you really need, it's minus 20 dB, whatever this is in dB, and you need that to be omega naught. And then the phase going from 0 to minus 90. All right. But I've kind of gone over that kind of thing a lot, and it's in the notes. The high pass filter, you could just say is the opposite, right? Plus 20 dB per decade, whatever the high frequency gain is, omega naught, right? For the time, right, that's the step response for a high pass. That's the step response for a low pass. This is very hard to get right in MOM. And so I end up having to go back and you know, put it right. So in my open math, there's the upload, I mean, in Canvas, right, there was the actual exam assignment and then the upload assignment. So in the upload assignment, I will have given some notes and then entered in a score that is actually your final score that I need to transfer over. But yes, that means it's graded. Now I really can't discuss anybody's exam until I'm done grading because that's just a task I have to do first, right?
So what, you have everyone's actual scores already?
I'm sorry, I couldn't quite hear.
So you have everyone's actual scores already?
What I'm hearing is, do I have everybody's scores ready?
Everybody's final scores.
No.
Okay.
No. I have 5 people, maybe 10 scores are done. I would show you in Canvas, but then you'd see your score. I can't publish people's scores, right, publicly, right? But let me just say is that when I'm done grading, you'll get an email. I'm done grading. If you need to discuss your exam, send me an email or something, okay? But you should also get a notification when something changes. All right. Now, a lot of the convolutions were really, it was either a high or a low pass, right? And I guess the thing is if I put in a step response and I get some kind of rounded shape, right? Okay. Where, you know, the slopes of these things are reduced one way or another, right? Even if it's this, because even though there's discontinuities here, it's not the same level of discontinuity, right? That makes it a low pass, right? But if I kind of am detecting an edge, right? Start at zero, go to something and come back, right? And also that means all the inverses are true, where if I can go here, down and back, right? Here, down and up. That's just an inverting low high pass. It's not, it's still a high or a low pass filter. Okay. Now really what we had for number 5, right? There was you got one Bodie plot, all right? These were the low and these were the high, right? And you got 4 responses, all right? And I believe the input was like this. Now, really, all you have to do is look at that, because that's a step response, right? And so if that thing is rounded somehow, maybe faster, right? One is going to be rounded in a slow manner. The 5 tau is going to be bigger than the other one, right? So if tau is bigger, omega naught is smaller, right? So this is the slow, and that's the fast, right? That's how you could tell between the low pass features and then the high pass, right? One's going to take a long time to dissipate. One is going to take a shorter time, right? That's omega naught, which is 1 over tau, right? So it's inverse. The slow one, the one that takes a longer time. So this is slow, and that is fast. Now in the reasoning, okay, just saying that looks like a low pass filter, that's not really reasons, right? You can talk about the shape, right? That it's high pass filter, low pass filters are evening out these curves, or they're getting rid of high frequencies, right? And that step certainly has a high frequency, all right? And that high pass filters detect edges, right? Or they're trying to calculate a slope. And so since the slopes are 0 here, the outputs goes to 0. Low pass filters pass DC. So when I put in a DC signal, well, it's going to stay constant. It doesn't decay to 0. Now in here, right, I should say in here, The high pass filter will eventually kind of try to be the slope, right? Because that's what they also do. Somebody mentioned something about, they said, well, that one looks like it has more drag. And that wasn't a term I'm familiar with, unless drag means you're pushing this out. I assume that's what you meant and gave you credit. Although it wasn't, like, to me, a standard word, okay? But maybe, you know, if you write kind of what's going on in the picture in your PDF, it'll make it a little bit easier, all right? Because I don't want you to have to just parrot what I say. And so maybe that drag is a great word for you, right? Just help me, all right? No, don't be sorry about your own terminology. But on the other hand, I am trying to tell you how it's talked about in industry so that people know what you mean, right? That's a good one, Emmanuel. In the Army, they'd say, I know you're sorry. Your way is a lot nicer. So that being said, oops. So I put this in the email, right? And I'm just going to mention this rather briefly because we have, you know, it is in the syllabus, but we have our midterm 1, we have our midterm 2, and then on the final, we have final M2 midterm 1, final midterm 2, and then what I might call final, right? And if the score on this is bigger than that, we replace it. If the score on this is bigger than that, it gets replaced. This is the last third of the class, so there's nothing really to replace, and it does not go the other way. The final exam is cumulative, and it's what can you do all at once. Sorry. There's 2 midterms. The final exam has 3 parts. And if you look in Canvas, you'll see it. Midterm 1, so it's 3 questions on midterm 1, 4 questions on midterm 2, and then 3 on the last part of the semester. That's one big midterm. But because these questions are similar to or come from midterm 1, these questions are similar to or come from midterm 2, well, if you do well here, I'm going to assume you figured it out, and then I replace these scores. For grade percentages, please see Canvas, okay? All right, the final exam has 10 questions. Midterm 2 is 5. It will be less mom dependent because you're going to have to draw a schematic, and there is no way at this moment in time that my open math can do that. All right, so yeah, to answer your question, Jacqueline, so here's the thing. Let's say, let's do a Bodie plot. Let's say you put in this, and the answer is this. All right, mom will give you points, but that is not a Bodie plot. You're not gonna, one is not gonna get the job or pass a job interview if you just draw a straight line like that, or even you just draw a straight line like that. So no, it is possible for points to go down, right? However, if you, let's say in my open math, you did that, right? But then on your PDF, you did it correctly. Oh, I'm going to check, I'm going to take that. That being said, I might make a mistake and not see that, right? So if you think I've made a mistake, that's okay. Like, Professor, you said that the magnitude wasn't right, but I really think I drew it properly, right? Because you can go and take all that Python code you learned and generate all the answers to your exams, and you can check your work, right? So if you think I've marked it incorrectly, just let me know and I'll go and look, because maybe this is the PDF, right? Maybe I missed it, right? But yeah, it is possible that your points would be reduced. All right, I try not to do that, but you know. The everybody should have gotten comments. Sometimes I forget to save them, right? But if if you have a score in your uploaded thing and you see no comments, then I forgot to click submit, and then just let me know and I will give you the comments, okay? But yeah, if you have 100%, well then no, you're not going to get any reasons why you're wrong because you were 100%. Okay? Well, no, don't say that in public. Okay? So anyway, again, it's there's still a human element here because you are human and you're going to be human on the job. And if we could automate this process 100%, well then you wouldn't need us, right? You just hire MyOpenMath to do all the work for us. Okay. Anyway, just send me an email because I'm not going to remember this. Okay. All right. Now the chair did talk to me about what is it called? Tutoring. Okay. You should have gotten an email from me where to go for peer connections. All right. What I've noticed though is that my emails tend not to be technical questions. It tends to be other things. All right. But really, a quick email to me, right, can be a pretty good way to get some help. However, if it's LT Spice or Python, please send the file, okay? Because I'm only going to ask for the file, and then by that time it might be too late, right? A picture just doesn't really do it, because sometimes there are some weird things that go on where a picture could be hiding the problem, right? And I like to verify if my answer is correct. Let's say, oh, here's your problem, right? Well, I can't verify it unless I have that file, right? And sure, people who have asked me things, I will say, can you set up the problem? So if you say, how did you get the answer? Okay, a better question would be, you start it, right? And then show me where you're stuck. Because otherwise you're just going to get the same speech, which I guess is, in my mind, I think I explained that question perfectly, right? And so if you don't tell me where you're stuck, I'm only going to give you the same speech that didn't work the first time. All right. Now, I know maybe some people feel more comfortable going to a peer, and I can totally understand that. I was deathly afraid to go to my professor's office hours because I thought you know, he might have his doubts about how ignorant I am, but God, once I open my mouth, then he'll know, then they'll know for sure. But it was never like that. And eventually I got over it. So, you know, we'll go from there. Now, also, I think I tend to go off of email trying to answer your questions just in time rather than holding formal office hours. If you really want formal office hours with Zoom meetings, I can create a time for that. But just send me an email that you'd really like that, right? Also, I have, well, no, that, all right. I do try to, but what would happen, like when I did run a workshop, right, is nobody would come, right? Or I would have office hours when I wasn't an advisor, and I'd be waiting and nobody would come. So I thought, well, the students would rather just email me, all right? Now here's the other thing too, is let's take this problem, right? Sure, I would like to see how you started. But what if, you know, it's just isn't clicking yet? You don't even know where to start. At that point, we probably need a face-to-face Zoom thing, and then I can kind of go along, right? And bring you through it and have a review, all right? Where if it's an email question, I can't answer how to solve that all in one, especially because it would be in the notes, but I'm not opposed to going over what you might consider review material. No, I have no problem with that. It's just in class and email is tough, all right? But I will tell you that the people who tend to get A's are the ones that are contacting me all the time for things. All right, you know, what about this? What about that? Also, we're going to do more in-class activities, and so you will learn to make friends. And like I've said before, that's our secret weapon for success. All right. I did want to go over advanced summers today, but I know there's maybe some questions you guys want to ask. I'll just throw the door open to any questions. Yep.
So, Professor,
Yes.
if I have a question about my what's called my PDF test,
Yes.
do you want me to hold on that on emailing you, or you want me to just do it now?
If you could, like,
Okay.
once I'm done grading, I should say, I am done grading. Now, if you have a problem or you need a clarification, you can email me. Because what might happen is my email will go to like 500, and then I might just lose it. I mean, not lose my temper. I mean, just lose the email.
Okay.
Okay.
Is there any way, if we have some time, we could go over the number 4 just one more time? Like which one would be, which example would be what kind of filter?
You know, I have to do the advanced summers.
Yeah, no worries, no worries.
Nick, right?
Yeah.
Okay, no, because and it could be I might need to do a little video on that. It's one of those things. I have gone over it, but in a 75-minute lecture, it could be really hard to find out where I went over it. And so sometimes a quick, what does this mean, is good to have. But that would be a great office hour question. Okay.
Sounds good.
Which in, okay. Actually, I'm gonna mute you because somebody's eating something. Sorry. You all. All right. Okay. Okay. Oh, hey Rudy. In my notes, I try to show how much I take off, or how much we're taking off for each thing. But you know what I think, because what I'm doing is in my open math, I'm actually changing the grade there, and I'm going to see if I can open that up to where you can see it very accurately, how where the points were calculated. Okay, but that's something I probably have to do a little bit better. Okay, but I am trying to do that. Okay, now, so we have been doing really filters. And here's the thing, why do I show this filter a lot? Well, it's really very useful, right? And I'm going to do the low pass. The high pass is really just switching these two. And the thing is that this is, it's very common. Many times, this is the only filter you need, right? And as a result, it tends to be an interview question. No, I'm not just teaching you how to pass an interview. This is really used, and therefore it's an interview question, right? But many times people, right before a job interview, will tell me what to study, right? And question 3, definitely, right? Now, there's other filter designs, right? And you've seen already where if I can, right, I can have this, and then I can even have it going into a high pass. Right? And so now I have a second order filter. And if the RCs are the same and different, it's great. The thing is, though, is just something, all these poles are real. What does that mean? Well, I'll tell you. Okay. So if this is the real part and this is the imaginary part, all our poles are here, right? And if they were 2 at the same spot, you'd actually just say, you put the squared symbol, right? Because that means there's 2 there. Now, why don't we have poles out here? That's later on in the class, actually. All right. Why don't we have poles at 0? Well, we do, and that's the integrator, right? But the thing is this really limits our design space. And there's filters where we put the poles here, and to get better filter characteristics. Again, better filter characteristics is a lot of what the rest of the course is about. I'm trying to tell you why we're going to do something, right? So, and this is just one pair of complex poles would be a second order system. And so this structure, although very useful, can't be used in every case. And so if I had a transfer function, something like this, where I could have s to the 4th plus a4, s4 plus. Okay, this is a different kind of transfer function. All right, everything is in ranking polynomials. All right, where the transfer functions we're used to, right? You have s plus b, you know, maybe s plus a, maybe it's squared, maybe you have another one. Of course, these would just cancel out, right? And in that Python code, it was, you gave it in pole 0 format, right? And these numbers, if you could make them complex, would actually show this behavior. But this circuits can't make complex poles, all right? Or you have a system you want to implement in op amps that it just can't do that. Now, what you actually do you see this 1 over S? That means I've made an integrator circuit, I'm just not drawing it out, right? I make another integrator circuit, I'm not just drawing it out. Another integrator circuit, and I'm just drawing it out, right? And then and again, you don't have to write this down. This is really coming up. But again, I really need to show you why I'm doing something, because it does deviate from the book a little bit. Okay. Now, inside of this is really this. Okay. So inside of each one of these is an inverting integrator. But notice all of these need to be inverting. And so what happens is this is actually minus S, which is, then I don't want to invert it. This would be minus times minus positive 1 over S squared. I do want to invert it, and so on and so on. And this summer, right, you want to just be able to add and subtract independently, all right? And so we need a summer that is compact and doesn't use a lot of op amps, right? Because let's say I want to add, let's just say A minus B. All right. And I can only use the inverting topology. Okay. I'm going to call that. All right. So if I put the B voltage here, sure, I'm going to get B, RF, RB minus. But then how do I get a positive A? I need to invert A. Okay. All right, so now, right, this would be minus A R2 R1 times minus RF RA. The minus signs cancel out, and then I can independently set that. So the problem is that if everything was subtraction, then that'd be fine. All right. But when you're mixing it up, all of a sudden I have that extra part. And that extra part, just to do an inversion, takes up a lot of board space. All right. So really, what I want is something that in one stage can add and subtract. Okay. In the book, they do it like this, as if op amps were free. And sure, some op amps at 73 cents are free. But some of you who ended up having to use a more expensive op amp in your lab, all right, some of those op amps are $2 a piece. And you might say that's not so bad. But in consumer electronics, $2 is a lot. And it takes up physical board space. All right. So, if we're all trying to have a smartphone that, is thin or of a certain size, and you're sucking up board space just because you got an extra op amp, that's not good. So hopefully I've convinced you why you need to do this. All right. But I'm going to lead you through it a little bit. Sorry, I just started reading the chats. Yeah, I had a meeting with the administration, and they called me a geek for having a low pass filter up for my Zoom picture. Yeah, the filter I showed, if the cutoff frequencies were chosen properly, that would be a bandpass. And are we focusing on negative feedback configuration for just now? Yes. In fact, in this course, if you ever find yourself with positive feedback, you kind of have to fix it to make sure that it's negative feedback. But there is a device. Oh, actually, Marielle, the Schmidt trigger we used over the summer for the summer bridge actually used positive feedback.
Yep.
Okay. Okay. Now let's. All right. Well, let's have a little bit of review. All right. Now, to actually, again, setting up currents and doing a nodal analysis and solving for this as if you'd never seen this configuration before isn't really what this course is about, right? I recognize that the inputs are coming in on the negative side, the feedback is negative, right? And that if I use superposition, right? And I set, I set that to 0. Oh, V out would equal VA RF RA minus, all right? And then if I set A to 0, same thing, all right? Now here's the thing. If you're struggling with what I just said, that superposition, and why it might be too hard to use KCL, that's a good office hour conversation, all right? Because sometimes I've noticed is people try to use KCL to remember what this circuit does, and it's just going to take you too long. Also, as a designer, right, this inverting summer is like, it's like you're an artist and you have to do a painting and you need certain colors, right? And so this is the inverting color, all right? Now, so this is a non-inverting summer, but it's a little bit trickier. But let's take this node and call it Vx. Well, you can tell that that's a non-inverting gain stage, right? So V out is going to equal 1 plus RFR1 Vx. Well, what's Vx? Well, let's do our superposition. So if VA is the input and the voltage is measured with respect to ground, right, that voltage division is going to be RB in parallel with RF, RA, RB in parallel with RF, right? So Vx due to A is that. All right, do superposition the other way, and Vx due to B is now remember, this is the input, this is to ground, and so now RA and RF are in parallel. Sorry, I'm running a little bit out of room here. But the important thing is this part goes in here. And then, maybe you would have seen it, right? But if all the resistances are equal, all right, well, I'm going to stop with that thought. So here's the thing. You might say that this is a bit complicated to deal with. And if I want a particular if I want VA to be multiplied by 10, added to VB multiplied by 20, these equations are kind of hard to use. But you can see that really it is possible to make a non-inverting summer. You just might think the algebra is a little involved, all right? Where the non-inverting case, oh, the algebra is dead easy, right? But the thing is, and just let me finish this thought, is that we can and I'm going to draw this a little better on the next page, right? A, B, C, D. We can make a summer that subtracts A and B and adds C and D and can set the gains independently. And there's actually, if you keep in mind certain things, can actually do this relatively straightforward, all right? But you can see, I'm trying to tell you where it comes from, right? You have inverting summers, non-inverting summers, right? And then you can combine them. And then by, again, I'm going to show you, if I set up two conditions on this circuit, one of which is you have RF right here equal to each other, that you can do this independently. And if you can do that independently, then all these sums, some of which are going to be negative and some are going to be positive, and all these constants will be different, right? You can independently do that with one op amp rather than adding an op amp every time you need an inversion, all right? Because here, this would be minus 1 over s, then this would be plus 1 over s squared, then minus 1 over s cubed, plus 1 over s to the fourth. And so, again, where that's coming from will be later, but just to show you that it's really needed. Okay. I'm going to go over this a little more. That was more where it's coming from. You're not actually going to derive it. Q, I don't get your question. And I know you're not Q, it's is it Korean? Anyway, I'm sorry, I don't get your question. So balancing out the op amp, you're going to see that that's exactly what we're doing, and that's a good phrase, because we will make sure that the gains balance. And so it's probably better just for me to show you an example.
Professor, I have a question.
Oh, sure.
On this previous schematic that you have two RFs. Is it necessary that they needed to be equal? If so, what's the reasoning?
Okay. I think these notes are posted, all right? And I am trying to show that these equations work, all right? And I'm just going to scroll through, and it's not that I'm trying to blow you off. It's just saying that it's a little bit much to go through that whole derivation, all right? But it actually gets really intense, okay? And what I found is that it doesn't matter. But what happens is it makes it easier. So the important part, again, what I'm about to talk about, is that the gains balance. But when I'm designing things, I try to use as many of the same part as once. So rather than have, so if I'm, if RF is going to be 100 kilo ohms here, then I want 100 kilo ohms here rather than some other value that I have to go by and keep a track of, okay? But it can, it's not obvious, right? And it was, and I don't think I ever proved it. This was just proving that it works with the same RF. And then this kind of idea of, well, I can see that it works. Okay, I hope that, but no,
Okay.
it makes sense.
So is it because we are accounting some sort of op-amp behavior, or it's something else?
Straight from that math.
Okay.
I mean, that you saw the math I was scrolling through, right?
Briefly, but my question being is that the application-wise, how to interpret that math in application so we
That's
can
what I'm
build
about
our
to.
intuition.
That's what I'm about to do.
All right.
Okay. But your question was, does RF have to be the same? And no, it doesn't. However, it's better to use the same part. Okay.
Okay. Thank you.
Okay. Okay, Nick. Yeah, I thought I had uploaded it. I'll do that after class. All right. And so, oh, it is there. Oh, good. Anyway, all right, I'm gonna ignore chat a little bit right now. Sorry. So let's say we want, right? That means the gain of A is equal to 1, and the gain of B equals -1. And here's the rule, right? Let's try to put the, so the rule is gains, the positive and the negative, have to sum to 0. Well, in this case, right, it already does, right? 1 minus 1 equals 0. So actually, I don't have to do much else at this moment in time. But so VA is going to be the positive one. So here's my generic structure. All right. So I have VA, I have RA, and then there's nothing else, right? So then I can just delete these. Then I have minus VB. Okay, so And then there's nothing else that I need, so I can just kind of cross out or delete the other resistors, right? And now, because I'm using this structure where I have an RF here and an RF here, again, they can be different values, but you need a resistor here, all right? And so gain A is going to be RF divided by RA. And I'm not quite sure why I switched colors, but and so gain B will be minus RF divided by RB. Now notice, because we have this RF here, you could think of it as kind of canceling out the RF up there, all right? And with the gains being equal, right, I can use these equations. So now if I want to design the circuit, I tend to use RF equals 100 kiloohms, right? Because it minimizes the noise and trying to minimizing the current flow as much as possible, all right? So if the gain is 1, then that means in this case, RA equals 100 kiloohms. RB equals 100 kiloohms. So then all I have to do is put 100K, 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 and 100K there. And then I'm pretty much done. All right. Now, what if we wanted V out equals 2VA minus VB? All right. So the gain A equals 2, gain B equals minus 1. All right. Now, I'm going to show you how to fix that. But essentially, we want this equal to 0. So we have to add GD, gain dummy, to make that work out, right? So if I want this to be sum up to 0, I actually have to add something with a gain of minus 1 times VD, which the way I'm going to get around that is set it to 0. So let's start with drawing the structure first. I know people got to go. I'm just going to finish this example, okay? Okay. So really, right, if the gain is 2, and that equals RF over R1, right? That means R1 equals 50 kiloohms. Again, because I tend to start with 100 kiloohms. All right, so that's good. GB equals minus 1 equals minus 1 RF over R, oops, that should have been A, RB. And again, we get back our 100K. And not only that, but the GD was -1. And so now you might say, well, you just added a voltage there, right? You really wanted this function, and now you're getting another function. Well, the way around it is you add that resistor, but then set it equal to 0. And what happens is that now this, like if you were doing superposition, you'd set both of these to ground, and then you'd have RF, the gain would be 1 divided by RF, RB in parallel with RD, and then it would cancel out whatever was going on down here, and it would work, okay? That's probably enough for today. Right, Nick, it's 0. So the dummy voltage is 0. Otherwise, it would change the circuit. Okay. So in these notes, right, I go over the theory of it, and then I do example after example. And pretty much oh, that's the derivation, but almost every case is there, okay? And it's pretty formally done. So I guess, so am I just arbitrarily choosing RF? For your first design, in some sense, yeah, a lot of times you might arbitrarily choose a value, but then you might find that your design doesn't work because what if I was trying to find an RA with a particular gain, but that RA was below 1K? For other reasons, that's resistances in these circuits below 1K isn't a good idea. So I might have just kind of done it wrong. Now, sure, based on experience, I find that 100K is kind of optimizing a lot of things, all right? But you could easily use 200 or 500. But if you use 10K or 50K, you'll find that a lot of the other resistors become small so that they don't, you get values of resistance that don't make sense, okay? But yeah, many years ago, I probably just pulled 100K out of my head thinking it was a good idea. And then as I learned more and more, I realized that that was the way to go. But sometimes it's not right. And I have to change it and then redesign things. Okay.
Question.
Yes.
So you said you're picking at this resistor values for some reasons. May we know what are those reasons? Like, what have you learned based on your experience, you know, in terms of picking this resistor
Okay,
values?
all right, so let me write it down because I did say it, but maybe, right? So one is minimize current, all right? But it's not minimized in the sense that it's the smallest, right? But if I have V, right, I, 100K will keep that current small. Well, then why not use 10 meg? Well, there's something that you might not know about, is that resistors can have a capacitance. Real resistors have a capacitance in parallel with them. And if this is too big, okay, it can start to act like an antenna and you're picking up signals from everywhere. Now you can buy on DigiKey 10 mega ohm resistors. You can buy 100 mega ohm resistors. Those applications are probably for something else. All right. Also, remember, let's take, this is RF. That's A and that's B. Remember that superposition where VA is RB in parallel with RF, R A plus. All right. If I choose a function generator, right, that has 50 ohms series resistance, right, and this equivalent resistance, right? So if B is a lot smaller than RF, right, it's going to be B. Now, sure, that total resistance, what am I driving, right? That would be RA, RB, and RF. If this network is around a K, it will still cause errors based on that 50 ohm, right? So in general, you try to keep this higher than that. And so if I started here at 1K and I wanted gains, RB would be less than that. And so I could end up with like an equivalent resistance of like 50 or 100. So by starting at 100 kilo ohms, it makes sure that when I'm done scaling everything and things are in parallel and series, I'm not getting this, right? Then there's another reason, is that many op amps can only supply like 20 to 40 milliamps. So if there's an op amp driving this and the resistances are too slow, you can have an issue there. Now,
So
I just want to double check something. Also, at the end of those notes, I kind of talk about that a little bit, okay?
Okay, so when
What's
you
your
talk
question?
about minimize current, is that current the bias current, or it's something else that we're trying to minimize?
I heard your question, I'm thinking. Okay. Sometimes with bias, some people call these resistors, you're biasing the op amp, okay? Other people would say, I'm configuring the op amp and these are signals, okay? So, but regardless, this output is a signal. And so the currents that make that output what it is are the signaling currents. And if you make them smaller, then you will use the less current that flows, the overall power will be reduced, okay? Bias is many times used in a different way, but I have seen people call these resistors as bias resistors, okay?
Okay. Hard, Prof. I'll digest
Oh,
that.
oh no, and those are great questions. And let me tell you, it is very hard to find that information because people will tell you, oh, just do this, and they'll never tell you why. And it's taken me probably,
That's why
it's
you
taken
use
me,
the data sheet.
right, right. But in general, what happened is I was doing something and the circuit didn't work. And then I went back to the data sheet and then realized why. And so a lot of the things that we talk about in class are mistakes that I've made that I feel you really need to know. And the way I learned it was by trying to do realistic engineering solutions to problems, right? And then I know this is what's necessary and this is what's not necessary. But this thing of this being an antenna, people just say it, but they don't necessarily prove it.
Okay.
Okay?
So we'll try to learn from your mistake. How about that?
Yeah, yeah. Make brand new mistakes. All right, I know people got to go. At least this will be recorded. All right, take care, everybody. Have a good, good weekend if I don't hear from you.
Thank you, Professor.